In statistics, correlation and regression are both words used when commenting on how well a set of data keeps to a given trend or pattern when displayed on axes, for instance. This trend could be linear, that is to say that the data points make more or less a straight line, or it could be non-linear, when obviously it's not a straight line, however we can still say that there is a pattern because those data points may follow a good mathematical curve. They're not just randomly appearing anywhere all the same. We will, of course, in a moment, therefore, be looking at the different kinds of correlation and how we can interpret a regression line, that is to say, what is mathematically the line of best fit for that given data set, assuming that their correlation is indeed strong enough to warrant it. However, before that, let's first take a look at the two types of variable that could be giving us this data set in the first place. Now, if you've done any of the sciences, you may have come across the terms of independent variable and dependent variable. And then here in maths, or I guess in other places as well, you may hear them instead referred to as explanatory variables and response variables. In either case, the independent or explanatory variable is the variable that is causing whatever is happening. It is the thing that is changing and thus getting us different results as an outcome. Meanwhile, the dependent or response variable is what is measured afterwards at the end, or what is caused by the explanatory variable. So for instance, if one data set was looking at how CO2 emissions from cars varies depending on the fuel consumption of the engine, the fuel consumption would be the explanatory variable, while the CO2 emissions would be the response, because we'd be saying that the usage of the fuel, that's what causes the CO2 to be produced and emitted. It's not the emission of CO2 that causes the fuel to be used up. If you want, you can think of it as in a timeline, which would come first, which would come second. The one that comes first is the explanatory, the one that comes second is the response. When it comes to then just plotting that data, therefore, unless the question makes it very explicitly clear it wants it the other way around, you should put your explanatory variable on the x-axis and your response variable on the y-axis. When you have that and you've made a scale if you need to, you then plot the data points and you will be able to judge their correlation. If your data points are making somewhat of a straight line, it doesn't have to be 100% perfect, so long as it's very clear that they are making a straight line more or less from the bottom left at some point to the top right at some point, you could describe that as having a strong positive correlation. Meanwhile, if it is still going from the bottom left to the top right, but it's not as clearly a defined straight line, that could be a weak positive correlation. If there really is no pattern at all, if your data points just seem to be all over the place, there's no correlation. And then kind of in the reverse, if we're now starting at the top left and going down to the bottom right, if there's something of a straight line but it's not absolutely defined, that would be a weak negative. And then if it's going from the top left to the bottom right in what is very clearly more or less a straight line, then that is a strong negative correlation. Now beneath each of these labellings I've also put these inequalities in red. In each case, this R is referring to the correlation coefficient, basically a numerical way of quantifying the strength of that correlation. This could be used in the event that the question doesn't give you any of the actual data points or the scatter diagram to work from. Instead, it's just talking about the scenario, then mentions that this data R equals 0.7. Let's say the number is going to be between -1 and 1. For 1 is a perfect positive correlation. That would be if they actually were exactly on a straight line going from bottom left to top right, and then -1 being the perfect negative correlation, sort of exactly on a straight line going from top left to bottom right. Anywhere really for the R value between 0.5 and 1 you would describe as a positive correlation, a strong positive rather. Anywhere between 0 and 0.5 would be a weak positive. 0 itself would be when there is no correlation. Then between 0 and minus 0.5 would be your weak negative, and between minus 0.5 and minus 1 is that strong negative. Whether you're able to tell it from the scatter diagram or you are told what the R value is, if the bits of data have a strong correlation, be it positive or negative, we can then justify using a regression line, which, as I said before, is like the mathematically best line of best fit. Now, in the new specifications, you shouldn't need to work out the regression line equation itself. It should just be given to you. Just a heads up, if you do start looking at older papers for practice, you may find certain questions where you need to work it out, so you shouldn't need to in this case. So they'll give you some equation, and you may just need to identify what certain numbers signify in that case. So here, this is pretty much like the y equals mx plus c. Obviously, we've got our y here, you've got your x here, and the b would be in the place of the m, and the a would be in the place of your c. It's just if they've put them the other way around, but because it's addition, that doesn't make a difference. As such, your a is your y-intercept, and your b is your gradient. Now, when it comes to interpreting the regression line equation that they give you, it's not going to be enough to just say, oh, it's the y-intercept, oh, it's the gradient. In any kind of question we need to interpret in terms of a scenario, you need to be using language that directly relates to the variables at hand. To just give an example as a reference point, let's say that the value of a painting was described by y equals 1.27 plus 0.45x, where y is the value of the painting in thousands of pounds and x is the number of years after it has been painted. Well, if we were to ask, well, what does the 1.27 tell us? What does it signify in this case? We would say that that means that the painting had a value of £1,270 when it was first painted. Meanwhile, what does the 0.45 tell us? Well, it tells us that every year that passes, the value of the painting goes up by £450. Because, well, that's what the gradient's telling us. Every time you go along one, the y-axis will go up by this amount. So here's this number that's on its own. What did you start with? What would that mean in the context of the scenario? The gradient, we're saying for whatever the x is standing for every one of these, the whatever the y stands for goes up by that number. Just for another, if you had had that y equals 246 minus 21.8x, where in this case the x will refer to the number of builders working on a project and y refers to how many minutes it should take in total to complete that project. So where we have the 21.8, that's saying that for every extra builder the total time it takes should go down by 21.8 minutes. And the 246, oh, well, again, that should be the y-intercept. That should be that it takes 246 minutes at the beginning, but that would seem to be when there are 0 builders. And there can't be 0 builders. And this is just one of the examples of how there are limitations to these regression line models. Yes, they are mathematically the best line of best fit you're going to get. It is the line that is on average closest to all of the points, assuming that they are close to being a straight line anyway. But firstly, depending on the scenario, the equation of the line could suggest values that just don't logically make sense. Like in this case, it would give values for time it takes for when nobody is present. Or it could even give negative times eventually. If x got big enough, the answer to this equation would be in the negative, and that's saying, well, they already completed it before they even started. Also, potentially, it could allow for decimals of people, which again, we obviously can't have. So that's just something to bear in mind. When you have your regression lines, they aren't going to be perfect for every single value. Think, how well does it make sense in the given scenario? Is it possible that this data would go on for infinity? Now, even if within the scenario it would actually make sense that it could go on to infinity, that's not to say that you should anyway use your equation therefore to work out such astronomically big values. You shouldn't even use it to work out values that are even only a small bit above what you already have. Let's say we go back to this painting example here. Let's say the data set which allowed us to get this regression line had been taken every year for the first 10 years. Right? So we've gone year 1, year 2, all the way up to year 10. And now we wish to use this regression line to predict what the price of the painting is going to be at year 15. Now the problem is that while we have had a steady increase of a graph here like so as a straight line, hence why we can get a regression line, the fact is we don't know what's going to happen after that 10-year mark. For all we know, yes, that trend is going to continue and we are going to continue to have this straight line going up here. But quite possibly instead we're going to have that the price then starts to increase more rapidly, or potentially the price tends off and even starts to go down again, or maybe even the price just starts to fluctuate wildly. The point is we don't know what's going to happen because it's outside of our data set. Therefore, we would be extrapolating, and extrapolation is unreliable. So in general, extrapolation is where we use the line to predict values that are outside of that data set. It'd be fine to try to use the regression line to try to work out a new data point that's inside the given range. That would be interpolation, so that's perfectly fine. Let's say that you wanted to estimate the value at 5.5 years. Yeah, you could do that. So long as the value that the question is mentioning isn't outside of what given range there is, you're good to go. Fail to meet this criteria, however, and if the question is asking you to comment on the use of the equation for such a calculation, you will have to give a negative response about its appropriateness. Alright, so these are pretty much the commentaries you can make on linear regression questions. With that established, let's now move on to non-linear examples. To be clear, the linear side of things is more to do with the AS maths, and this non-linear will be more for the A2, just to make that distinction here. Now, in these kind of questions, you may still find what seem to be the same models of regression lines as what we just had previously. We could have here that y equals 9.101 minus 1.12x. This very clearly is in the same form of equation as what we had on the previous screen. Well, what's different this time is that x and y aren't actually the variables being studied. In fact, what we're really looking at is t and s. It just so happens that for whatever reason, t and s have been deemed not the best things to try to plot on a graph. So instead, they've been first coded, and we've discussed coding when we first looked at the likes of standard deviation and taking means and so forth. So this linear line here is the true data having been transformed into something that is a straight line. Well, the purpose of this question, therefore, for you is to turn this back into its original true form. And we've got down here at the bottom that this is the form that they want you to get it into, where s equals ab to the power of t, where s and t are those variables, and then a and b are constants to be found. This, therefore, is going to rely on concepts from pure maths, because as we can see, we're going to be working with logarithms. So whenever we're looking at this non-linear regression stuff, you may just want to bear in mind you want to be kind of familiar enough with those ideas as well. To start off the actual working then, let's just substitute the x and the y for the expressions that we know them to be the same as. So here, x is just straight up equal to the t. Clearly, didn't feel there was much need to change that one other than the fact that they were coding it in two different letters, the more recognizable ones, x and y. So this is now just going to be 1.12t here, and that's still 9.101. However, instead of y, we can now say that that's going to be log of base 10 of s, which we could just write as a regular log without any base number because that's then assumed to be 10, but we'll just want to be explicit here. Well, how do we then get the s out of this logarithm? Because obviously we can see we need to get the s on its own. Well, if we reverse the logarithm, undo it, we raise the entire other side as a power of this base of 10. So you end up with 10 to the power of 9.101 minus 1.12t. Now, because of the powers at play here, because there is a minus, that would usually indicate that we're about to be dividing. However, because this is multiplied in the answer we're trying to get to, I'll make it a multiplication instead. We'll say that this is the same as 10 to the power of 9.101 times by 10 to the power of minus 1.12t. Because remember, when we times the same base number together, that just adds the two powers together in what would have been a single power. So we can now just do the reverse and split it up into this multiplication. From here, then, there isn't really much else we would need to do. We can simply say that this will again be s times by, if we want, we can isolate this further, just more explicitly as its own term. But then here, we've now got powers, or terms in the power that are times together. We can separate those out slightly if we want, by saying that that will be 10 to the power of minus 1.12, then put that in brackets, and say that that in turn is to the power of t. Because if you have power bracket power, that's the same as multiplying them. Therefore, we now have what our a is and what our b is. You could put those into your calculator and work out what they exactly are if you wish, but you can just leave them there as powers of 10. We could also comment in this example that our a term here, like the a in the other question, kind of coincidentally, that's going to be your starting value. For when t is 0, that's going to make this entire b to the power of t term just equal 1, because anything to the power of 0 is 1. So it's 1 times a, so a is whatever you're starting with. And then for b, we'll be saying that for every one of whatever t is, s gets multiplied by this b value. And with that, you may wish to acknowledge once again that there are some limitations to such a model. For instance, this is an equation would keep on going into infinity, whereas likely in the scenario it wouldn't make sense to keep getting bigger and bigger and bigger. But other than that, you have your equation that you can then interpret thusly. And with that, therefore, I'd just like to see if you could get along with this last example on your own. So once again, we're starting with a linear expression in terms of y and x. So y equals 23.14 plus 1.618x. And we have that x is actually the log of q plus 2, and that y is the log of p. And this time, you're actually looking to get it in this form here, of p equals AQB. You'll notice, to the power of b. You'll notice compared to last time, the second variable that we have from our equations up here isn't the power this time, it's the base number. The power is one of the two constants. So again, just think about what we did in this first example on the left, think what you may want to do on the right in a similar manner, and how it is going to end up slightly differently just to end up in this form here. Pause the video, have a go for yourself, and then press play again when you're ready to compare. Okay, so to start off with, we'll begin like we did last time by switching out the x and the y for the expressions that they give us. So now on the left hand side we have a log base 10 of p, and that's going to equal the 23.14 plus the 1.618 times by log base 10 of q and then plussing the 2 afterwards. From here, we may wish to expand this bracket. So again, the rest of everything that's on the left is going to remain the exact same. However, we're then going to have on the right, so plus 1.618, and then just the logarithm. But now afterwards, that'll be plus 3.236. Then we can just bring together those two as both regular numbers, so we just add them together. So again, log base 10 of p. That's now therefore going to be 26.376. Still add the 1.618 log of q. From here, because we'll be looking to get the p on its own, we can now raise this right-hand side as a power of 10, which then in the next step we can specify is 2 lots of 10 to each of these individual powers, then just times together. So 10 to the power of the 26.376 times by 10 to the power of 1.618 log q. Here at this point, because once again we have terms that are times together in the power, we can separate them out as 10 to one of them as a power, brackets, then the other power on the outside. This time I'm actually going to put the logarithm in, keep that next to the 10, so we'll have 10 to the power of the log base 10 q, then afterwards now put that to the power of the 1.618, again keeping everything else that was. And then finally we can just say that 10 to the power of log base 10 of q, well that's just going to be the same as q, because if the base of the logarithm in the power is the same as the number that has a power to it, it basically eliminates it, leaving you with just what was inside the logarithm brackets. So that's now just q to the power of 1.618. Again, the rest is still p, and then the 10 to the power of 26.376. And thus we can just confirm that your a is that 10 term here, and then the b is the 1.618.